Today, on How It's Made. Golf balls. Getting into the swing of things. Furniture handles. We had to use some pull to get into this factory. Parking meters. Before time's up, you'll see how they make them. And room dividers. We bring you wall-to-wall coverage. Different types of golf balls deliver different results. Highly skilled golfers often use what's called a wound ball, a ball made of rubber thread wound tightly over a core because its flight is more controllable. But most people use what's called a two-piece ball, a ball whose core is covered in a dimpled material. Today's golf ball has really come a long way if you consider that the early ones were made of feathers. This is what's inside now, a bouncy rubber. They mix it up with other chemicals to make a hot batter, and then roll it out like a pie crust, cooling it between two huge steel drums. Next, they push the rolled-up rubbery sheets into this machine called an extruder. There's a ram inside and it forces the rubber through a die. This makes shapes that resemble large marshmallows called slugs. A conveyor belt sends them to a compression mold machine. Here, a worker positions the slugs in a steel mold. The slugs often vary in color depending on the type of ball being produced. When the door closes, the bottom part of the mold presses up into the top part, applying over a ton of pressure. This is a shape and bake system, because inside this mold, the newly rounded rubber is cooking at 167 degrees Celsius. Baking it for 13 minutes hardens it. Then, after it's cooled with water, a worker places a piece of slotted plexiglass over the mold. This holds down the leftover trimmings so that only the ball shapes get picked up by the vacuum. He peels off the excess rubber for recycling later. The marshmallow-shaped slugs have now been transformed into a solid golf ball core. A robot transports these cores to another mold. A ram pushes melted plastic through tubes and into a mold cavity. This forms the outside shell of the golf ball, complete with the dimples that will help the ball travel farther. This is an inside look at a ball with its new shell. This injection molding system generates 4 dozen golf balls every minute. The new balls are on the move. They roll into a bin which funnels them to a golf ball elevator. They're on their way to get cleaned up. Look closely and you'll see little pieces of leftover plastic on the ball shells. The next process will get rid of that. This is an automatic miller that removes the excess plastic. This is a golf ball before milling. And here it is after the flecks of plastic have been removed. Next, robotic arms shuttle the golf balls toward a chute entry. This is a quality checkpoint. If the ball is not smooth and uniform, it won't go through this hole. Now, a wheel rolls the golf balls towards a stamping machine. Robotic arms carry silicone pads to an etched steel plate. The pads soak up ink from the etched plate and transfer it to the balls. The pads brand each ball with a player number, the company name, and the model type. Then beams of ultraviolet light harden the ink. They dump the balls into a bin, but they funnel some balls over to another stamping machine. This one does custom logoing. Now that's a stamp of approval. Next, an automated machine sprays the balls with polyurethane while they rotate atop spindles. The polyurethane protects the ink logos that have been stamped on the balls. Robotic arms carry the wet golf balls to a drying rack where they cook at 66 degrees Celsius for 5 minutes. Then they're done. And that's the technique behind the golf ball. It's up to you to explain your golf technique. Imagine a dresser with antique-style brass pulls. Now imagine that same dresser with country-style wooden knobs, or funky plastic knobs, or sleek handles in stainless steel. The decorative hardware on a piece of furniture or on cabinetry dramatically affects its look, so changing it is an easy and inexpensive makeover. How would we get a grip on things without knobs and handles? But they're more than something that can open doors for you. The many styles add to the appeal of our furniture. To make a handle, an electrical hoist drops big chunks of zinc into a melting furnace. At 427 degrees Celsius, metal quickly turns into liquid. It's so hot you'd lose a finger if you touched it. Automated arms move an iron pot full of the liquid to a railroad car which takes it to the next stage. Here they pour the liquid metal into another furnace that's just as hot. This is called a machine furnace. A hydraulically driven cylinder pushes the liquid metal through a system of nozzles and pipes that run through the furnace. It carries the liquid metal to a die. The die shapes the handles cookie cutter style. Water flushes through the die. This cools down the zinc and it hardens into a handle shape with a lot of extra molding that they're going to have to get rid of. So now that they've cooled, it's safe to touch them and remove some of that waste. A worker snaps some of it off and tosses it in a bin for recycling later. And the handle shapes go into a separate bin. But there are still some little bits of waste on the handles called overflows. So a mechanically driven spinner tosses the handles around and knocks off any overflows that have been missed. It's a lot faster than picking off those little pieces by hand. A worker dumps the handle shapes into a bin. They're starting to look like something you could really hang on to. A similar die casting system is used to make knobs. But the knobs come in 2 interlocking pieces. They place them on a turntable and fit them together. Then a 4-ton hydraulic press presses down on the knob, and that pressure seals them. They pour a mixture of water and oil on the knobs to cool and lubricate them, while an automated machine drives a screw into the back of the knob. This makes a thread pattern inside of it, so it can be easily screwed onto furniture later. Now they plunge the handles into a chemical bath. The chemicals help to conduct electricity. This process is called electroplating. The handles are negatively charged. The brass particles in the water are positively charged. They attract and connect, and this causes the brass plating to form. They dip the handles into the chemical wash twice and then rinse twice. Next, they dump the brass handles into a vat of acid. This oxidizes it, blackening the finish to make it look antiqued. This brass pull has aged 100 years in just a few minutes. Next, they funnel the handles into a big round polisher. It's called a bowl vibrator. The handles are mixed in with steel ball bearings. The machine vibrates and the friction from the ball bearings polishes the handles. Now those antiqued brass handles have a shinier finish. Sometimes they use ceramic pellets in the polisher instead of ball bearings. They spray soap and water into the bowl to lubricate the handles and allow them to move freely. This gentler friction results in a different finish. The polish on the handles will be brighter. Now they put a handle into a clamp. With air pressure, it puts the squeeze on the handle so that it hooks into a back plate. When the pressure is released, the fit is snug. A front and back plate gives a handle a more elaborate look. They buff up a knob with a cloth polishing wheel that's mechanically driven. This process gives knobs and handles a certain gleam. It's the finishing touch. So now you have a handle on how furniture hardware is made. The Beatles wrote a song about lovely Rita, the meter maid. But try finding anyone else singing the praises of those uniformed patrols who ticket your car when your meter expires. Parking meters have been around since the 1930s, and ever since then, drivers, especially those caught without change, have been cursing them. It's time to unlock the mysteries of the parking meter and find out just what makes it tick. First, the low-tech part. The time limit label goes onto a zinc dome-shaped plate. Then a worker sprays lubricant onto various parts of the motherboard that contains computer circuitry. After he snaps the board onto the plate, he screws it in. Then he fastens another dome-shaped plate onto the back, sandwiching the motherboard between the two plates. The worker hooks the board up to the power source, the battery pack. And he tucks the pack into a special compartment so that it's secure. Then he plugs a programming device called an X key into prongs protruding from the motherboard. The key feeds software to the motherboard inside. When numbers appear on the screen, it's programmed. The next piece, called a smart chute, also has computer circuitry. It analyzes the coins as they fall through the meter. It can tell the difference between Canadian coins and American ones, and even recognize coins from other countries. He puts the chute into a protective plastic casing and plugs it into the protruding prongs that were used earlier to program the meter. The two boards make a connection and can now communicate to one another. He clicks another zinc plate over the coin chute and adds a stainless steel coin slot for added protection. This card is a radio frequency probe that detects how much money is in the meter as well as maintenance information. Just how good is this meter at analyzing coins? Well, a Canadian nickel and a British 20 pence are roughly the same size. Put in a Canadian nickel and you get 3 minutes. But try the 20 pence. Nothing registers. The meter treats it like a plugged nickel. The meters are now in an environmental chamber. This chamber replicates the most extreme climate conditions. It's a test to make sure they're ready for life on the street. Now it's time to make a lock. He puts a zinc alloy lock plug containing brass tumblers into a miniature lathe. The lathe spins rapidly on its axis while pressing against hard steel blades. The blades cut the spinning lock tumblers to the appropriate length. The result? A lock plug that has brass tumblers of different lengths that can't be opened without the correct key. Here, a worker places the lock barrel in a vise to give a better view of the lock system. As you can see, it turns easily with the key. But vandals beware! This lock is designed to be tough to pick. Next, he inserts the lock into the bottom of a coin can that's made of plastic. He closes it and then puts it on what's called a sonic welding machine. It emits high-frequency sound vibrations that actually melt the rigid plastic, welding the top and bottom pieces together. Now these coins will be really tough to get out without that key. Next, he brushes a second lock system with a lubricant and adds a hard steel shield that will resist attempts to drill into it. This lock goes onto an iron door which will be part of the vault that contains the coin can. He brushes the lock assembly with another lubricant to make the locking operation smoother. Then he installs a rubber gasket along the frame for the meter dome window. This gasket seals the dome and protects the electronics from harsh weather. He places a tough plastic window on the gasket and tops it with a zinc strap. He screws all the pieces together. Then he places the iron case that will hold all the mechanics on top of the vault containing the coin can. He attaches the windowed cap and strap assembly with hinges. And there's a third lock to help protect the electrical components of the parking meter. After a check for fit and function, he installs the actual mechanics. This means it's all systems go. The parking meter is ready for the street. Later, the coins can be collected without even opening the plastic coin can. This special receptacle activates the lock at the bottom of the can. Once turned, the coins deposited into the parking meter drop into the receptacle. If you need to section off part of a room, there are many types of room dividers that can do the job. Accordion doors routinely divide meeting rooms. Sliding walls made up of multiple panels can easily split a large reception hall in half, or partition an office in no time at all. This particular company makes two types of room dividers: sliding panels called operable walls and accordion doors. Both have built-in soundproofing. The folding mechanism at the core of an accordion door is called a pantograph. It's made of flat steel bars riveted together in a crisscross configuration. A worker tightens the rivets just enough to hold the bars in position without impeding their movement. Then he inserts pins along the top and bottom, securing them with steel retaining rings. The pantograph is custom built to expand to the precise width of the door they're making. The pins attach to the covers that will later sandwich the pantograph, forming the accordion door's surface. To make those covers, they first make slats. This automated machine hot glues a band of cardboard onto a band of steel. Then a series of rollers progressively folds the sides upward, forming a steel edge around the cardboard. Finally, the machine cuts the continuous band into slats, whose length is the height of the accordion door they're making. Now workers pair up the slats, connecting them with cardboard strips. They feed each pair into a glue machine. The slats come out adhered to a soft and flexible type of paper that's tear-proof. Next, workers connect 6 pairs of slats to form a panel. Then they glue on the decorative surface, in this case, commercial quality vinyl. To block sound from passing through the space above and below the accordion door, a worker glues a felt and vinyl strip to the top and bottom of each panel. After lining the inside of each panel with acoustic wool, a soundproofing material, the worker gathers the number of panels required for the door's width. He attaches them using industrial-strength steel staples. Then he slips U-shaped steel channels onto what will be the door's inside folds. Using an air-powered machine called a serter, he presses the channels tightly in place. Now he installs the pantographs. The height of the door determines how many. Using steel retaining rings, he locks the pantograph pins into holes on the channels. The second cover goes on the same way. After this, workers apply a metal trim to finish off the front and back ends. They also install a handle for opening and closing the door. The door hangs by wheels attached to the top pantograph. Operable walls are made up of several sliding panels. For each one, workers build an aluminum frame, then install a soundproofing mechanism, a crank-activated aluminum seal that juts out to fill the gap above and below the panel. To make the front and back faces of each panel, workers begin with a sheet of gypsum board. To one side of it, they glue a steel sheet that's at least 1 millimeter thick. This provides soundproofing. To the other side, they glue a decorative surface, in this case laminate, a thinner version of the material used for countertops. A machine called a pinch roll applies pressure to ensure the laminate adheres well. Workers slide the face into the frame, fill the middle with acoustical wool for soundproofing, then slide in a second facing. They close up the bottom, then test the retractable soundproofing seal. The last step is to install the wheels that run along a ceiling rail. An operable wall can have one or many types of faces, from fabric, mirror, or galvanized steel to blackboard, marker board, or even cork bulletin board. Today, on How It's Made. Paving asphalt. Let's get this show on the road. Marshmallow cookies. The facts behind the snacks. Loudspeakers. A product that relies on sound construction. And electronic door locks. We'll visit a factory that's no turnkey operation. Asphalt is a black liquid substance that's a byproduct of processing crude petroleum. Asphalt is a key component of waterproofing and insulation materials and roofing shingles. But its best known use is for paving roads. Asphalt cement is a byproduct of crude oil, the key ingredient they mix with crushed rocks and other minerals to make paving asphalt. So production begins at the paving plant's quarry, where some 15 meters below ground, workers driving heavy machinery collect boulders of granite that have been blasted off the rock walls. Trucks transport the rocks to the paving plant, which is right on the quarry site. They dump their cargo into the primary crusher, a machine whose steel jaws crush these big rocks into pieces smaller than 20 centimeters. It takes mammoth force to crush solid rock. The flywheels that amplify the motor's energy weigh more than 6 metric tons. The primary crusher empties onto a mobile conveyor belt, which transports the crushed rocks to an outdoor storage area. When it's time to make the asphalt, the rocks travel via conveyor belt from the storage area to a screening building to be classified by size. There, the rocks tumble downward over a series of inclined screens whose largest holes are 10 centimeters big. What's too large to drop through goes to a secondary crusher that reduces the rocks to 10 centimeters or smaller, then sends them to a third or tertiary crusher that further reduces them to 2 centimeters or smaller. What's small enough to pass through the screens bypasses the secondary crusher and goes directly to the tertiary crusher. After this last crushing stage, the largest stones are 2 centimeters in size. Everything smaller than 5 millimeters goes in one pile. That includes stone dust created by the crushing process. Stones 10 to 14 millimeters go into another pile. Stones 5 to 10 millimeters into another. Trucks transfer material from each pile to separate compartments called feed bins. Exactly what goes into the paving asphalt depends on what's being paved, but generally, these are the 4 ingredients. Sand, stone dust, 5 to 10 millimeter stone, and 10 to 14 millimeter stone. The ingredient proportions vary according to what the paving asphalt will be used for. Stones, along with sand and stone dust as fillers, usually make up about 95% of the mix. The remainder, added later, will be liquid asphalt cement. Each bin releases a specific amount of material onto a conveyor belt running under it. The belts lead to a main collecting belt that dumps the ingredients combined onto yet another belt that leads to a dryer. The drying process, which takes about a minute, removes all traces of humidity. This will enable the materials to bond better with the asphalt cement. Screening equipment then re-separates the dried ingredients, making it possible to precisely weigh out the required amount of each one. Everything then goes into a mixer. As this demonstration shows, the mixer blends everything thoroughly. Then it's time to pump in hot asphalt cement. Oil refineries make asphalt cement from what's left over after they've processed crude oil. The paving mix contains about 5% asphalt cement. This is what happens inside the mixer. The hot asphalt cement binds the ingredients in about 30 seconds. The result is ready-to-lay paving asphalt. The mixer empties directly into trucks destined for the paving site. There, a paving machine will spread the hot asphalt on the roadbed. Then, a compactor roller will pack it down. The asphalt cools and hardens in about 1 hour, depending on the weather. The next time you bite into a marshmallow cookie, you can thank the ancient Egyptians. They invented marshmallow candy by thickening honey with sap from the root of the marshmallow plant, a herb that grows in salt marshes and along large bodies of water. Modern marshmallow contains gelatin instead of sap from the mallow root. The snap test, to make sure the coating is hard and thick enough. Then, the taste test. If you've got a sweet tooth, doing quality control in the marshmallow cookie factory is your dream job. To make a batch of dough for the cookie base, they mix wheat flour, salt, baking soda and powder, cornstarch, whey powder, and potassium sorbate. Then they add several liquid ingredients. This one causes a chemical reaction, making the biscuit lighter. This cream-colored liquid is vegetable oil shortening. This transparent liquid is glucose fructose, a sweetener. The ingredient proportions are also a company secret. From the mixer, the dough goes into a machine called the chipper. It shreds the big blob into pieces about the size of the cap on a highlighter pen. This makes the dough more manageable for the next machine, called a rotary mold. Inside that machine, a large roller flattens the dough pieces, forming them into a dense sheet about 1.5 centimeters thick. It then presses the sheet against another roller, whose surface is a cookie mold. The factory uses the rotary mold machine for many different types of cookies. It simply installs the appropriate roller for the cookie in production. For marshmallow cookie bases, the mold cavities are round. The bases exit the rotary mold and make their way onto a moving baking sheet that transports them to an oven. The baking time and temperature are, once again, top secret. The baked cookie bases exit the oven and move onto a conveyor belt that transports them to a cooling area. Once they cool to room temperature, the bases go into a machine called the base feeder. It lines them up like marching soldiers to receive their marshmallow filling and chocolate coating. The process does require military precision. Factory technicians have to adjust this machine daily to ensure to-the-millimeter accuracy. A portion of filling has to land perfectly centered on each base, finishing off in a curled peak, this brand's trademark. The company won't divulge how much marshmallow filling goes into each cookie, nor will it reveal its marshmallow recipe. But marshmallow is usually made from either corn syrup or sugar and gelatin. for the final layer, the chocolate coating. Not only are the marshmallow and base covered in hot melted chocolate, the base floats in it, which coats the underside as well. Built-in air jets blow off the excess. The chocolate hardens inside a cooling tunnel. How long that takes and the tunnel temperature are, you guessed it, classified information. As the cookies exit the cooling tunnel, a quality control worker does spot checks to ensure the coating is thorough, hard enough, and thick enough. On the packaging line, the cookies go into plastic trays. To keep up to speed, the workers have to grab 4 cookies in each hand without breaking the coating. The trays pass through a machine that wraps them in plastic film. This keeps the cookies fresh and also prevents them from falling out of the tray. Meanwhile, another machine assembles the boxes, first folding and gluing one end shut. Once workers load the trays, the machine glues the open end closed as well. Then, with the go-ahead from quality control, the box's next stop is the cookie aisle of your local supermarket. Loudspeakers take an electrical signal and turn it into sound. The key to it all is a magnetic wire voice coil and a permanent magnet that attract and repel each other. As the coil moves back and forth, it rapidly vibrates a flexible cone. This vibrates the air in front of the speaker, creating sound waves. Loudspeakers contain at least 2 magnet and cone assemblies known as drivers. They're typically housed in a box called the speaker enclosure. To build the internal magnetic structure, the factory begins by cutting 2 plates of iron, each about 13 millimeters thick. They go one at a time onto a lathe. First, the machining tool smooths and evens out the surfaces, getting rid of the marks the saw made. Then it cuts out a small hole in the center of one plate and a larger hole in the center of the other. Next, they cut a smaller and thicker round piece of iron called the core. A reamer bores a large hole through it. They apply super high-strength epoxy glue to the core and to the back plate, the plate with the smaller hole. They glue and screw the pieces together because the bond has to be strong enough to withstand intense magnetic pull. They glue a foam filter in the hole to ensure the vibrating cone doesn't draw in dust and cause internal damage. Now they spread glue on the narrow end of what's called the metal basket, a die-cast aluminum frame that will hold the magnetic structure and cone. They screw the front plate, the plate with the bigger hole, onto the glued surface. Then they glue the underside of the front plate and one side of a ferrite, a ceramic ring made from iron powder. After adhering the ferrite to the front plate, they apply glue to the other side of the ferrite, then flip the basket over to attach the back plate. The core fits through the large hole in the front plate. They insert shims to center it while the glue dries. After screwing terminals to the basket, they put the entire structure they've just assembled into a magnetizing machine. With 600 volts of direct current, the machine creates positive and negative poles, transforming the magnetic structure into a permanent magnet, meaning it has a constant magnetic field around it. Now they wind the voice coil, the electromagnet that will interact with the permanent magnet. An electromagnet is an object that generates a magnetic field only when there's a current running through it. They wind enamel-insulated copper wire, gluing it to a rigid plastic sheet. The positive pole of this voice coil will be attracted to the negative pole of the permanent magnet. The negative poles will repel each other. The key is that the voice coil's poles are constantly reversing position because the electrical current running to the speaker is an alternating current. meaning it switches between a positive and negative charge several times per second. This makes the magnets attract and repel each other continuously, causing the voice coil to move back and forth rapidly. This vibrates the cone, which creates sound waves. After slipping the voice coil between the front plate and the core, they glue on the bottom suspension, flexible fabric rings that move with the voice coil and prevent it from rubbing on the magnetic structure. Next, they glue the cone. It's usually made of cardboard, plastic, or metal. Then they solder the electrical connections. The current coming from the amplifier travels by wire to the two terminals. The terminal wires connect to the voice coil wires. After making sure the cone moves freely without rubbing, they glue on a rigid cardboard cap to keep out dust. The last step is to take the speaker for an audio test drive. They connect it to a machine that transmits different frequencies. They make sure the movement of the voice coil and cone isn't obstructed in any way. Then a computer device analyzes the sound wave the driver sends out. Two-way speaker systems have two drivers in each enclosure, a woofer and a tweeter. A woofer has a large cone that vibrates more slowly for low frequencies. A tweeter has a small cone that vibrates quickly for high frequencies. Three-way systems have a third driver with a medium-sized cone for the mid-ranges. At most hotels, room keys are a thing of the past. You're more likely these days to be given a key card. When you arrive at the door to your room, you swipe or insert it to unlock the handle and get in. Because the room number doesn't appear on the card, this system is far more secure than door locks with a keyhole. The metal case that houses the door lock's mechanical and electronic components is called the housing. To make it, they begin by melting zinc ingots. To melt zinc, you have to heat it to about 390 degrees Celsius. Die casting machinery then injects the molten zinc into molds. Between injections, sprayers coat the empty mold cavities with a release agent, the industrial equivalent of greasing a baking pan. A built-in cooling system hardens the metal, then a trimming die cuts off the excess zinc around each piece and in the openings. Meanwhile, the electronic circuit board, the brain of the lock, takes shape. They call this the pick-and-place machine. It picks up the 60-odd electronic components and places them in the right position on each board. This computer-guided machine installs 15,000 components per hour. Next, the boards undergo what's called wave soldering. A mix of molten lead and tin surges up from underneath, fusing the components in place and creating electrical bonds. Then both sides of each circuit board get a coat of silicone-based sealant. This protects the components against the elements. Back to the housings now. Workers lubricate them with grease, then apply what's called a sleeve bearing, a nylon bearing that enables the handle to turn smoothly. Next comes the drive tube, onto which the lever will be assembled on the other side. There are several clutch components that link the lever to the latch. Swipe the right card and they permit the latch to retract. After applying more lubricant, they install an override that enables the hotel to open the door with a key if, for some reason, the electronics malfunction. They install the circuit board and connect it to the various parts of controls, such as the clutch motor, which they install next. Now they close up the completed housing with a steel backplate. This protects the components inside from rusting. The last step is to insert a battery pack. It holds 3 standard AA batteries. The factory tests the lock using a test key card because the lock isn't yet programmed to work with a specific card. That's done after installation. Elsewhere in the factory, They assemble the mortise, the part of the lock that goes inside the door. When you lock up, the mortise's bolt comes out of the door edge and fits into the hole of a receiving piece called the strike plate in the door frame. They close up the mortise with a back plate. This demonstration shows how they install the mortise in the door. Once it's in, they screw a decorative plate on top. This is what the finished electronic door lock looks like. Key cards have instructions on one side, a magnetic data stripe on the other. They use a generic card to test every lock that comes off the production line. In the quality control lab, they subject every new design to several rigorous tests. They open and close 1 million times. They subject the lever, latch, and lock to repeated impacts. They also test lock function in extreme temperatures. These electronic door locks come in several metal finishes plated over the zinc, and even in a painted finish that simulates wood.
Today on How It's Made. Horse-drawn carriages, craftsmanship that's hot to trot. Artificial eyes, the product of artistic vision. Dog and cat food, it's not the slop it used to be. And mirrors, when image is everything. Nothing takes you back to the past quite like a ride in a horse-drawn carriage, a timeless vehicle in both appearance and construction. Building one, even today, still requires the expertise of several traditional craftspeople, from ironworkers to wheelwrights. The carriage's turning mechanism is a fifth wheel that's positioned horizontally above the two front wheels. Workers weld the fifth wheel to the carriage's steel frame, then weld the boarding steps to the frame. Until now, the frame has been positioned upside down. Now they turn it right side up to install the driver's seat. First, they measure carefully to ensure it's perfectly centered. Then they solder it in place. Once the frame is complete, it goes through an acid wash to remove any residue. Then they buff the solder joints to smooth out their surface. The carriage has drum brakes. Workers install them onto the axle, then assemble the steel springs that make up the suspension, and bolt them onto the axle as well. Next, they connect the brake line. Then they install the whole assembly under the carriage's frame. Like in the olden days, they make the wheels out of wood. Metal isn't flexible enough to withstand bumps in the road. They use ash because it's a very hard wood that also doesn't rot easily. Workers position 16 spokes around a steel hub. They clamp the spokes in place, compressing them against the hub. Then they secure them with nuts and bolts. Next, they mark the spokes in two places. The first line shows how long to cut each spoke. The second line, how far to dowel the end. To form the dowel, they first shape the end into a cone. Then the cone into a dowel. Those dowel spokes will fit into corresponding holes they now drill into two semicircular strips of wood. The strips form what's called the felloe, the round part of the wheel. Workers tighten the hub, then press a steel band called a channel against the felloe. They cut the channel to size, then solder the ends together. Then they buff the joint smooth. Next, they drill 8 holes through the channel, then using a tapering tool, thread the holes to fit the bolts that bind the channel to the felloe. Finally, they tighten the bolts with a special gun. The tires are made of rubber. They contain 2 steel wires to hold them in place over the wheel. Workers grease the channel of the now painted wheel so that the tire will slip on easily. Then they mount the wheel on the automated tire installation machine, which pulls on the wires, installing the tire tightly over the wheel. They weld the wire ends together using bronze solder this time for a stronger joint. Then, here comes the high-tech part, they bang the wheel on the ground 4 or 5 times until the distance between the tire ends closes, covering the welded wires inside. A tap of the hammer, followed by a final bang, ensure the tire joint is secure. Now they can mount the wheels onto the axles and install the axles under the body of the carriage. After testing the 5th wheel and the brakes, it's time to apply the finishing artistic touches. All they need now is a little horsepower. The ancient Romans and Egyptians fashioned artificial eyes out of painted clay. By the 1500s, Europeans started making them out of enameled gold, and soon out of glass, which remained the norm for hundreds of years. Today, most artificial eyes are made of acrylic. If you've lost an eye in an accident or to a disease, a specialist known as an ocularist can fit you with an artificial eye. You can get a ready-made model or a custom-made prosthesis like the one for which this patient's being fitted. No 2 people's eye sockets are the same, so the first step is to take an impression. After inserting the impression tray, they inject a material called alginate, filling the entire socket cavity. After 90 seconds, the alginate sets, and they can remove the hardened impression. They place the impression in a mold and pour in a type of plaster. When the plaster has hardened, they remove the impression tray and then the impression itself. What's left in the mold is a plaster replica of the socket. Now they put a wad of acrylic plastic dough into the mold, lock the mold into a press, and submerge it in a high-pressure curing unit for 25 minutes. Then they cool the mold in cold water. Here's the original impression compared to the acrylic model they've just cast. This model is called the fitting shape because they use it to fit and mark the positioning of the fake iris. They accentuate the markings, then attach a peg with a drop of wax. The peg indicates the natural angle of the iris when the patient is looking forward. Next, they add wax around the perimeter to enlarge the fitting shape. This excess will give the ocularist some play afterwards for the final sizing. Now they take this marked and enlarged fitting shape and make a plaster mold. They'll later use that mold to cast the actual artificial eye. But first, they have to make the iris. They take a curved black acrylic disc and paint it as realistically as possible with high-quality artist's oils. The patient has to be present so they can match the real eye. Next, they glue an acrylic cornea with an appropriate size pupil onto the painted iris. At this point, the artificial iris is 13 millimeters in diameter. If the patient's real iris is smaller, they trim down the replica to match. The iris then goes into the plaster mold, covered with white acrylic dough. After the same high-pressure curing process as before, out comes the artificial eye, covered with excess white acrylic. They trim off that excess and the peg, using a grinding tool and a cutter. This refines the shape and exposes the iris buried underneath. They smooth the surface against a grinding stone and verify the measurements. Then, using hard coloring pencils, they add finishing touches to the iris and draw blood vessels. They label the eye with the patient's initials, then apply an acrylic coating to seal the pencil marks. To create veins with some dimension, they use the same acrylic coating to stick on some delicate silk threads. Once they're satisfied the artificial eye is a perfect match, they seal the artwork with another acrylic coating. Once that cures, they polish the eye to a shine with a cotton wheel. The shapes and colors of artificial eyes are endless because patients' eye sockets and irises greatly vary, as do their scleras, the white of the eye. This artificial eye, or ocular prosthesis, is ready. The final step is to ensure that the fit is perfect. The patient's ocular muscles attach to the implant, enabling his artificial eye to move in unison with his real eye. So much for feeding Fido scraps from the table. Today's pet food is the stuff of sophisticated nutritional science. It's about protein, carbohydrates, vitamins, minerals, a well-balanced diet. Want to bet some dogs and cats eat healthier than their owners? The formulas for dog and cat food differ because dogs and cats have different nutritional requirements. Cats, for instance, need more fat and protein in their diet than dogs do. But the basic ingredients that factories grind up to make dog and cat food are generally similar. First, corn kernels. Then cereals such as barley, wheat, and rice. Workers weigh the ingredients, grind them in a mill, then combine everything in a mixer until they have an even and well-blended powder. A machine called the extruder transforms that powder into bite-sized pieces of pet food. It steam cooks the mixture, then forces it through dies at high pressure. The dies shape it, the way the tip of a pastry bag shapes icing into swirls or roses. Check out this dog bone die. As the continuous stream of shaped mixture exits the die, a spinning knife cuts it into pieces. The company has different dies to produce different shapes. This is a batch of round pieces. Next stop, a hot air dryer for 25 minutes. It heats the pieces to 149 degrees Celsius to draw out the moisture, then cools them at room temperature. Once the pieces exit the dryer, they enter a revolving drum where they're sprayed with fat and flavoring. The fat is designed to add food energy, while the flavoring gives the bland pieces an appetizing odor and taste. Appetizing for the pets, that is. The rotation ensures the pieces get coated evenly. From here, the pieces go into storage silos. When they leave the silos for bagging, the machinery screens out any crumbs. The pet food industry has made some interesting observations about the likes and dislikes of its four-legged clientele. Apparently, cats and dogs aren't crazy about food that's too dry, too hard to chew, or too mushy. If the pieces are too small, they'll swallow them whole without chewing and not digest them properly. But if the pieces are too big, they'll gag and get turned off the food altogether. In the packaging department, automated scales weigh the exact quantity per package. This batch is destined for 3-kilogram bags. The package sizes range from just 400 grams all the way up to 20 kilos. Shelf life is from 12 to 16 months, depending on the formula. Pet food experts say dogs and cats prefer food with a fattier content and a combined meat and cereal formula over just cereal alone. But too much meat flavoring can turn them off. Cats, as a rule, are more particular. They favor more acidic food, while dogs tend to have a sweeter tooth. And you thought kids were fussy eaters. No bathroom's complete without one, and any parent will tell you that no teenager can survive without one. Mirror, mirror on the wall, how do they make you after all? Well, how it's made is about to show you. But first, let's reflect on the history of mirrors. The earliest mirrors were curved pieces of highly polished metal, such as brass or bronze. They're even mentioned in the Bible. Then in the 14th century, the Venetians invented very crude glass mirrors that reflected off a metallic backing. They later perfected this technique using an amalgam of tin and mercury. Eventually, the secret of mirror making spread to other cities. By 1835, a German chemist developed the silver-backed mirror that we know today. A mirror starts out as clear glass. A robot lays each panel horizontally on a conveyor belt, which transports it to the washing station. There, sprayers blast the glass with water and cerium oxide, a powder derived from a type of earth. Rotating brushes scrub and polish both the top and bottom surfaces, removing oils and other contaminants. This washing process takes about a minute per panel. Next, sprayers rinse the glass with piping hot demineralized water. Demineralized because the minerals in plain tap water would damage the metals they apply next. The first metal is liquefied tin, which goes on what will be the back of the mirror. It allows the second metal, silver, to adhere because silver won't stick directly to glass. The silver is also in liquid form, mixed with a chemical activator. Within seconds of interacting with the tin, it hardens, and as it does, you begin to see a reflection. It's this silver backing that transforms clear glass into a mirror. Sprayers rinse off the excess silver, which gets recycled back into the system. The factory will seal this silver backing with 2 coats of paint. Paint by itself, however, isn't enough to protect the silver in the long term, so they first spray on a layer of copper. Sprayers rinse off the excess copper, Then the panel passes through a dryer at 71 degrees Celsius. This evaporates the moisture on the surface in just 75 seconds. Now the panel passes copper side up through what's called the curtain coater, a machine that runs a continuous curtain of paint across the conveyor belt. With its fresh coat of paint, the mirror then passes through an oven heated to 99 degrees Celsius. After 1 minute and 45 seconds, the paint is cured. Now the second coat of paint. There's no reason for the different color other than to differentiate the coats. The curing period this time is twice as long and at a higher temperature, 118 degrees Celsius. After an acid wash to remove any metal residues, they stand the panel upright to inspect it. If they find a fault, such as a bubble in the glass, they cut that portion out. The factory now cuts these large panels into whatever size and shape the customer has ordered, using a special mirror cutting machine that's precision guided by computer software. It scores the mirror using a carbide wheel. Carbide is a strong metal. To make round mirrors, the machine first scores the panel into squares. Then in each square, it scores a circle. Using special tools, workers separate the squares, then the circles. To make beveled mirrors, they use what's called the shape bevel machine. First, it carves out the edge, then polishes it to a shine using concentrated cerium oxide, a stronger version of what they used earlier to clean the glass surface before plating it with metals. Mirror factories also ship whole panels to shops that do the cutting themselves. A fragile feat that's certainly not for the superstitious.